It's a non-negative random variable. Yeah. Question?
I just wanted to say it's fine.
Yes. So, yeah. So otherwise, this makes no sense. All right. Yeah. No. As a matter of fact, for this inequality, yeah. Okay, you basically have to, bound that branch away. Okay. So this is again the scaling behavior. So let's get something that's a little bit tighter than that. And you've probably seen a proof of the Chernoff bound, but you probably haven't seen that proof. So this is probably the shortest proof that at least I know of. So it's possibly due to Sanjay Dasgupta. He himself isn't quite sure whether that's the first occurrence. There seems to be another paper which used the same technique. But anyway, it's a very elegant proof. So suppose we take the, okay, so who knows what the KL divergence is? Okay, most of you. So for those who don't, it's basically a way of measuring how different two distributions are in basically the expected value of P log P minus P log Q. This is quantity. And you can think of it as the extra number of bits you need to encode a sequence if the codebook is generated using P, if you then actually encounter Q. So it's basically the excess number of bits. Okay. So now an interesting question that I could try to answer is, if I have n independent coin tosses from a biased coin with probability P, now what's the probability that the number of times that I see, let's say hits here, will exceed n times Q? So I'm drawing from P, but I want to know, what's the probability that it'll exceed P to the point where it's greater or equal than Q? And the Chernoff bound, the original version is, and so this is a slightly stronger variant I'll show you in a moment, it's basically that we have e to the minus number of samples times the Kullback-Leibel divergence between P and Q. That actually makes sense because that's the number of bits that you need to use to encode that sequence. And so if the sequence is highly unlikely, you would expect that it's highly unlikely that you see that, that you see it. And so this is actually a very natural expression here. And there's something called Pinska's inequality. In its most basic form, it states that the KL divergence between P and Q is less equal than 2 times P minus Q squared. We're going to derive that in a moment. But for the moment, just assume that. And this is typically how you would see the Chernoff bound. But this is obviously tighter. So let's prove it. So let's look at the event that I see k times hits under probability Q divided by the same event under probability P. So actually that should be an equality here. But let's for the moment assume that Q is larger than P, otherwise it works out the same way. And let's say K is greater or equal than Q times N. Those are the events that I'm really interested in. So that's just binomial expansion, Q to the K, 1 minus Q to the N minus K. Same thing here in the denominator. Okay. Now since I know that K is greater or equal than Q times N, I can, and since Q is larger than P, replace this by Q times N here and there. Well, I can replace it here, that works out fine for that ratio. I can replace it there because there's minus K. Now, if you squint at that hard enough, you'll see that this is exactly e to the n times the KL divergence. Yep?
Can you explain why you plug in the Qn that's bigger than you plug in K?
Okay. So what I want to do is I'm interested in performing the sum over all the cases where I have n times Q or up to n many hits.
Yeah, I mean.
So therefore, and what I'm doing is I'm basically trying to look at the ratio of the probabilities of hits if they are larger than Q times N.
Yes.
That's sorry, yeah.
The question is why that function is like decreasing in K. So K dash gets smaller, you get a bigger number on the right hand side, right?
Okay, so okay, let's look at that. So Q.
That gets smaller. That gets bigger, but the other one gets smaller.
Well, no, here I have a minus k.
Yeah.
So we have a q over p, and here we have 1 minus q minus divided by 1 over p. And it's negative sign. So that should be. Okay, I think I got the inequalities wrong. Okay. Yeah. Yeah. Okay, P and Q are flipped here. Yeah.
Just one.
And well, in that case, what? So you can just. Okay, so basically, okay, well, the argument goes through. I mean, I've swapped Q and P. Thanks. Thanks for paying attention. This is great, actually. It'll be corrected in the slides when they come out tonight. Okay, so if you work this out, it'll give you e to the, n times KL divergence. Now, to complete the argument, what you're then doing is, you therefore get an inequality for the Q probability in terms of the P probability. And then you sum over all the cases where that excess happens. And so you can bound one set relative to the other. And since you know that the total, tail has probability less equal than 1, so this is what we do. So basically, here, K given Q is less equal than P of K given P times e to the minus n times KL P Q. And now we sum over all k's. K equals nq up to n. And this, of course, is still less equal than 1. And this is exactly my failure probability. That's basically the point that I want to bound. And I'm home. So that's how you can prove that tail bound. You can also prove it by a very different trick, where you take the expectation of the exponential of a random variable. So the way how you would have probably seen it is by taking the expectation over x of sum over I xi, and then use Gauss Markov on that. That's what you probably would have seen. This proof is, I think, a little bit shorter. Okay. Now, this is a very basic version. There are much more fun versions of similar types of inequalities, like packed-based bounds and so on. If you had a statistical machine learning class, that would be one thing that you could, for instance. Now, we sometimes need slightly stronger inequalities. So there's, for instance, McDiarmid's inequality, and it basically behaves very much like the Chernoff bound that I just showed you before. The key difference is that it's a bit more general. So what it does is it says, at least one version of theme, that if I have some function f, which depends on x1 through xm, that in this case, the probability of a large deviation between f of x1 through xm and its expectation being larger than epsilon is bounded by 2 e to the minus 2 epsilon squared over c squared. Okay? So we have the same correct dependence on epsilon, which may or may not be a good thing, but actually it's a bad thing. I mean, you could rather have something that goes like epsilon. But this c here is given by the sum over the changes that f experiences if I swap one instance by something entirely different. So a lot of stability bounds for learning algorithms are proven in exactly that way, by basically showing that if I take a single instance and I replace it by another instance, my estimate doesn't change by too much, and then therefore my error, my loss doesn't change by too much, and then I just sum over all those losses and I get a guarantee on the overall error that I'm going to experience. So that's how you get actually a lot of stability bounds, and we might encounter one or two of them later on when we actually have some learning algorithms to go upon. Yes?
For the xi prime, you mean for any xi prime?
Pardon?
For the xi prime in the...
Yeah. No, it's just the xi prime that was changed. I swapped a single instance, everything else remains the same.
Yeah, but that seems to be anything basically.
It could be anything from the domain from which the x's are drawn. And you're absolutely right, this could be a problem. So for instance, if the xi's are drawn from the reals, and this is a simple average, then this inequality doesn't work. So that's exactly why, for instance, for Höfting, you need an upper and a lower bound on these random variables, and then it's the size of the interval that calibrates the tightness of this bound. So you can fairly immediately check that averages, if f of x1 through xm is just the average, then by swapping out one instance, things can change by at most as much as those two values are different. And then it's basically that range that comes into this into this constant C. So that's a very simple thing that you may want to check. Who hasn't seen this thing before? Okay, good. Let's do it on the whiteboard. It's very strange. Once you've seen it once, before that it may look very surprising. So there's a wonderful tutorial on concentration inequalities by a guy called Gabor Lugosi. So have a look at his papers if you're interested in that type of reasoning. So these are very well written papers. He's also written a few books. But look at his tutorial on concentration inequalities if you're interested. There's in particular one paper by him with Boucheron and Bousquet. It's a great tutorial. It's probably way beyond the scope of what we need for this class, but it's really a great read. Okay, so let's pick a simple function. Our function is going to be the average. F of x1 through xn is going to be 1 over n, sum over I, going from 1 to n xi. Okay. Furthermore, I'm going to assume that xi is in an interval between a and b. Okay. So then, if I take one instance, remove it, and add another one in, what's the maximum deviation that I can get? Well, I can get b minus a. Because the interval from which I'm drawing the instances is bounded by b minus a, so that's the maximum deviation I will ever encounter. So therefore, I know that ci is b minus a. So therefore, it follows that c squared equals n, well actually it's b minus a divided by n, because we have the division here. So c squared therefore is, so I'm squaring all those terms and then multiplying any of them, I get 1 over n times b minus a squared. Right? Because that's exactly our condition here. And then we go and plug it in here. So we get the inequality that the probability of deviation is bounded by a to the minus 2 epsilon squared times, now the n was in the denominator, so it comes up here, divided by b minus a squared. That's exactly.
Is the n squared? Yeah.
No, there is no n squared term here. So the reason why you don't have n squared is because I had ci being, 1 over n. So b minus a over n. I square this, so I get n squared, but I now have to sum over n of them. So that cancels out, so that's why I have a 1 over n rather than 1 over n squared. By the way, thanks for asking. That's good. It means you're actually trying to follow the truth. I'm delighted about that. Thanks. But if you squint at that hard enough, so for our previous case where we had a binary random variable with 0 and 1 outcomes, right? We knew that b minus a squared was 1. So that goes away. Now epsilon was exactly the deviation between the true probability and the one that we want to bound away. So p minus q is epsilon. And then p minus q squared. So if you look at the previous slide, we had 2n epsilon squared. That's exactly the same bound that we get here. Okay. Now let's just look a little bit at the scaling behavior. So what we get is, we can just go and solve for delta. That's sometimes quite useful. And this is how you can get very scary, impressive looking bounds for, well, sometimes in papers it's useful to intimidate the referees. Okay, I hope no referee is present and will ever watch this video. But, okay, now joking aside, this is what you typically do if you want to get epsilon in terms of all the other terms. Because usually, you're going to be given some probability of accuracy, some failure probability, some delta. You want to figure out, what leeway epsilon you actually have. So you can just, take the log of that. So you get. So by the way, the factor of 2 here happens because we just symmetrically bounded things from above and below. And you can do similar things without the 2 and then get one-sided bounds, but it was just lazy game. Okay, so we get log delta over 2 is less equal than minus 2m epsilon squared over c squared. And solving that gives me epsilon is less equal than, c times square root log 2 minus log delta over 2m. This is the type of inequality that you will see in a lot of randomized algorithms, probabilistic analysis, somewhere appearing. So typically you would see a log delta term and some square root sample size term occurring somewhere. There's a high chance of that. Yep?
Why did you not bound the epsilon?
Why do I not bound what?
What's your motivation to bound the epsilon?
Okay, why would I want to get the bound on the epsilon? Well, what I would like to be able to tell is, suppose I have 1,000 users, so m equals 1,000, and suppose I want to make sure that I only screw up with 5% probability, so delta is 0.05, and suppose that I know by how much, let's say I'm selling ads for $1, so C might be maybe in the order of $1. I might want to know, how uncertain am I in my estimate of my revenue. So that's where you get the epsilon. So that's the accuracy parameter, and we'll actually look at a couple of instances of how accurately you can get things in a moment. But the nice thing, and this is the key difference from all the previous bounds, is that here we now have a log delta dependence. Before that we had a 1 over delta or 1 over square root delta dependence on the error probability. And that's not a big deal if delta is large. So if delta is in the order of 1/2 or whatever, then log x and x are comparable. But if that failure probability gets really small, then there's a big benefit in actually having logs. So there's an entire industry of people who do tail bounds. And it's probably one of the rather fun parts of, of machine learning and statistics, at least if you like that kind of stuff. So there's things like a Bernstein inequality, and so the interesting thing is that this can give you slightly faster rates for not so high levels of accuracy. So all those different bounds have slightly different conditions on the random variables, and under those conditions you can get better guarantees. And in the first approximation, if you want to prove something, you go through your catalog of maybe 10, 15 bounds, and you try to figure out which one fits best. And in most cases it won't be quite a perfect fit, so you may have to do a bit of assumption engineering and combine maybe several guarantees. That makes some of those proofs a bit more fun. So, as I already mentioned, you can, for instance, prove them through the Gauss-Markov inequality. There is a rather nice synopsis of some of these Chernoff bounds on Wikipedia. There is probably half a dozen of different Chernoff bounds that all go under the same name, sometimes with slightly different constants. So I found out about that a little bit the hard way when I was trying to reprove the Alon Matthias and Segedi sketch bound for next class, and I basically couldn't reconstruct one of their constants. And yeah, for instance, the Upfall and Mitzenmacher book have, I think, 3 or 4 Chernoff bounds, and the probabilistic method of Alon Spencer have another 3, and they work for slightly different conditions, so you want to be reasonably careful about which bound you use. Yep?
What is T?
T. Well, that should actually be an epsilon here. Thanks. Yes.
Should we have an absolute value of um minus mu there?
Then, well, for some you do. For this one you don't. So I mean, in some cases you only care about upper deviations. In some cases you care only about lower deviations. So, for instance, suppose I want to build a speech recognizer. Then I only care about the speech recognizer doing dramatically worse than on my training set. I'm not really worried about it actually performing better in practice, also because I know that this is usually not what's going to happen. In some other cases, let's say I want to do options pricing or financial prediction, I might actually really care about getting the value spot on. So for instance, if I'm betting on a deviation not being larger than a certain threshold, well, you actually care about the upper and the lower bounds. But in this case, you probably wouldn't be using tail bounds in the first place, but doing something a lot more fancy. So I think now's a good time for a short break, and then we'll look at how those tail bounds behave in practice, and, well, probably a little bit of bars and windows and so on.